So to start, we want to understand the evolution of the cold gas, the star-forming gas. And basically what we're trying to do is not just get a census of gas masses or whatever. We're trying to understand the critical diagrams of galaxy evolution, which in many of the talks we discussed this, so I don't need to go into this for sure. And what we've done is to assemble a database based on our own CO measurements, but also based on measurements from the literature using different techniques to measure the molecular gas mass in a sample of over 2,000 galaxies from redshift 0 all the way out to beyond redshift 3. And so we've used the CO technique, and this is our coverage in the star formation redshift plane. So we cover pretty well the main sequence. We have a lot of points at redshift 0 from especially from the X-cold gas survey led by Amélie Saint-Onge and Guinevere Kaufmann with the IRAM 30 meter. And these are mostly points from FIBS and other higher redshift CO surveys. We've also taken all the data we could from Herschel using the peak of the dust SED and doing SED fitting, which probably David will tell you a little bit more about in the next talk, to get a gas mass. Once you make an assumption for gas to dust ratio, you get gas masses this way. And unfortunately, we don't have Herschel anymore, but here you can see that we have quite a few sources, over 500 sources, I believe, from Herschel, mostly at the intermediate redshifts. And then more recently with ALMA, in a technique that Nick Scoville pioneered, you use the fact that the Rayleigh genes end of the SED of the dust SED is optically thin, and you can then, with a single measurement, which is very efficient, very fast, make an assessment of the gas mass that way. So what we've tried to do is take all these sources, use a consistent set of methodologies in deriving the properties of these sources, including the star formation rates and the stellar masses, and consistently then get the gas masses to get scaling relations of the depletion time, which you've heard about a lot yesterday, as well as the gas fraction. So what has this shown us? This is a plot that Chris showed you yesterday. This is the depletion time as a function of redshift. But what I want to point out here is not just the slope of the redshift. I'll get back to that in the next slide. These are all the points that we have. The green are the CO, the red are the Herschel measurements, and the black are the ALMA single point dust continuum measurements. And what I hope you can see here is that the three techniques agree extremely well. So the CO to H2 conversion factor, which has always been everyone's, oh, this is the biggest uncertainty we have in astronomy, I don't think that that's a problem for, at least at the massive end of the massive galaxies that we're observing. But even at low redshift, we have some low mass galaxies, and the agreement between the three different methods, three independent methods, is very, very good. So there is definitely the metallicity effect affects all three methods, because at low metals we also don't have dust, and then the dust to gas ratio is uncertain and all things like that. But I hope I can convince you that with 2,000 points, three independent methods, the three methods agree extremely well. So now let's go on to the scaling relations. First, the depletion time. We've talked a lot about this yesterday, why depletion time is such an important quantity to get a handle on. This is the same plot before that shows for all of our sources the trend with redshift. And as you can see, a pretty clear -1 slope. This is this decrease, this slope implies a factor of 3 decrease in the depletion time as you go from redshift 0 out to redshift 2. Now the Maddow plot, Lilly-Maddow plot, shows the star formation evolution of the star formation density is a 20%, is a 20-time fold increase from redshift 0 to redshift 2. So it's not that the depletion time is so much shorter, or in the inverse, that gas is forming stars more efficiently, which I think Chris showed you yesterday, is not the case. That's not the main thing that's driving this increase in star formation rate. So if you account for the trend in redshift, then we look at the residuals and we make additional fits. And this, what's shown here on the right plot, is a plot in the star formation, specific star formation rate stellar mass plane, color-coded by depletion time, where the low depletion times are up here and the longer depletion times are down here. And what you see is that as you go up in specific star formation rate, this is relative to the main sequence, there's a definite trend of the depletion time decreasing as you go up above the main sequence. Whether you want to call that a starburst or not, that's a semantic, that's fine, but there's definitely clear trend with a dependence of roughly minus 0.5. Once you account for that, though, we see very little dependence with stellar mass. There's no obvious trend here, and that's what Reinhardt told you yesterday. We really don't see a dependence on stellar mass with over 2,000 points at all redshifts. So that's our scaling relation with depletion time. Just a quick little semantic point, because a lot of people in the community or in the literature present everything in terms of the Kennecott-Schmidt relation rather than separating out the individual components. And I just want to point out, so here in blue we see all of redshift 0 sources. In red you see redshift 1 sources, or redshift 1 to 2 sources. And you see an offset. That's this decreasing trend here with redshift. So if you, in a Kennecott-Schmidt plot galaxies that have different properties, some are on main sequence, some are off main sequence, or if you plot things at different redshift, you'll get a superlinear slope. You'll come up with your slope of 1.5 or 2. But if you plot a given population, a given redshift, or main sequence galaxies, which is also what the local galaxy FANG survey or other local galaxy surveys have shown, you come up with a linear slope. So that's just sort of a technical point. How can you compare relations of depletion time that we're deriving with the more traditional Kennecott-Schmidt plots? Now, this mass independent turns out to be very, very important. Reinhardt also made this point yesterday, because that means the population that we cannot observe directly, which is the low mass, low metallicity populations, we can then make an assessment of their properties based on these scaling relations. So the second relation that we derive is one, how does the gas fraction evolve also as a function of redshift, specific star formation rate, stellar mass. And here, this is the plot of gas fraction. This is just, here is m gas over m star as a function of redshift. And what you see is there's a clear, steep increase as you go from redshift 0 out to about redshift 2.5, with a dependence, roughly linear dependence that goes roughly as the power of 2.5, with a flattening at higher redshift and a decrease even beyond that, which is all consistent with the bathtub model or the equilibrium model that we talked about so much yesterday. This is an interesting, because what it says is what you might expect, is that the gas fraction increase, what we're seeing, tracks as more or less the accretion from the halo. So this is a very nice a way of showing what the theorists have been predicting. So if you account for the redshift dependence, here we do the same thing with this plot, specific star formation rate, stellar mass, plane. And here is the gas fractions coded here. Now we see that there is also a decrease in gas fraction as you go off the main sequence, above the main sequence, and an increase in gas fraction as you go above the main sequence, and a decrease as you go below. So the gas fraction increases as the depletion time decreases, and this is what causes this increase in star formation off the main sequence. It's very interesting to go into the subgalactic scale to look at the physics of what's actually going on here, and that's what's coming in the future. The second dependence you see, though, is that the gas fraction drops at the high stellar masses, basically right at the Schechter mass. We see a drop. This has been seen at low redshift alone in the X-gas survey and in many other surveys. This is something that's also seen in the H1. And this may be related to properties of shutting down star formation, quenching, whatever you want to call it. So the scaling relation with gas fraction is a little bit more complicated, but with the steep increase with redshift, an inverse to the depletion time with offset from the main sequence, and then this drop with stellar mass. So putting this all together, the quantity that most of you who are working on simulations probably really want is the evolution of the gas density with cosmic time. And there's been two ways, mostly. There may be other ways in the future. The two ways in the literature up till now that have aimed to derive this. One is you stare at a piece of sky and do a deep field, count up what you've got, and make the calculation of the volume, the evolution of the volume with redshift. And that's been done with a large program with ALMA, led by Fabian Walter and colleagues. This is Aspects. It's also been done with the VLA and with lower J CO lines called Cold Z, led by Dominic Riechers. And our team has also looked at the blank parts of all of our hundreds of sources to get what we call the FIBS deep field. This is work that was done by Laura Lenkich as part of her PhD thesis at the University of Maryland. And what you find is this peak out at around redshift 2, and then this drop at the higher redshifts. But you can see the box sizes, there's a fair amount of uncertainty. Now, the fact that our scaling relations give us a mass-independent relation, what you can do is to take the cosmic star formation rate density plot and multiply it by our depletion time relation, and you get the same thing back out. And that's what this curve here shows with the rough uncertainties here, because we have so many sources. And you can see that the agreement is very, very good with the deep field techniques, but that one comes for free on the pointed observations that we have. So we would argue that if you choose your samples well and you know the characteristics of the galaxies that you're including and the scaling relations, together with the scaling relations, you get a very good assessment of the cosmic evolution of the molecular gas. Completely consistent with the deep field scanning technique, but it's sort of a freebie as part of the other research that you can do with these defined samples. So that's also reassuring. So just quickly, I want to end this part of the talk. How am I doing on time? Okay. Okay, good. With this plot, which Reinhard showed you yesterday, where we think we have a consistent picture now based on our scaling relations, which is the plot I just showed you here, the depletion time relation, the cosmic gas evolution relation based on our depletion time scalings. And then you see all the other, here's the star formation rate density, the accretion, the influx in the bathtub model is here in blue. The stellar mass increase here. This is the H1 density. from the various H1 surveys, also the absorption line surveys. And this is from the simulations of Romeo Dave's Mufasa surveys in his predictions of molecular gas. So what you see is that you see this strong increase at the early phases. You see a peak, as we showed. Now the peak is actually, in the molecular gas density, actually occurs at a lower redshift than that of the star formation rate. That's about 2, this is about 1.5. And what's probably going on there is that your early star formation rate, which has caused some outflows, that stuff is raining back in, keeping the galaxies a little bit more gas rich for a little bit longer time. But then you definitely see this fall off. At all epochs, the H1 dominates, even in the molecular gas-rich epochs. But the H1 is most likely coming from these outer reservoirs, which then may feed back into the galaxy and ultimately form molecular clouds and stars. The simulations do pretty well with the H1. Here's where there may be some discrepancy with the simulations, and we think that it's got to do with the fact that the feedback models, they really, you need a good feedback model in order to match the observations. So they're matching the observations pretty well at most of the times, but they have much more molecular gas in the early times than what we think we observe. And that may be related to feedback recipes. So I think it's a fairly self-consistent picture globally. So all this was done, global measurements, nothing spatially resolved. So do we understand things? I think the glass is half full. At a first order, I think we do. There's still some open questions at the lower mass. There's still some open questions at the highest redshifts. And those measurements are very, very hard to get, but I'm sure you will see refinements of these relations in the next years. But what we wanted to do is now to probe into the internal physics of the galaxies, also at redshift 2, redshift 1. You heard lots of great talks from Florent Reynaud and Omri and Avishai yesterday motivating all this. This is what we want. So what we have done with the newly upgraded Noema interferometer in the northern hemisphere is to construct an observatory-wide program called Noema 3D, which will ultimately entail 1,700 hours of time over 5 to 6 years. And this is in return of the extra funding that we were able to, from the Max Planck side, put into the upgrade of this facility. It's involving a large team of people who are listed here. And just quickly to tell you what is Noema, because I don't know that many people know about it. It's now 12 15-meter antennas. They're very large. They're very good at detecting point sources, faint point sources. Because we're based in southern France in the Alps, we're not based on Châtenay-Tor. We are mostly limited to the 3, 2, and 1 millimeter bands. So we're not doing sub-millimeter work on Plateau de Bure. But we have exclusive coverage at the lowest end of the 3 millimeter band currently, and already we have 16 gigahertz of bandwidth per polarization, which is twice the instantaneous bandwidth of ALMA. That's about to be upgraded again with a dual band capability next year, which will allow us to observe 2 bands simultaneously, which will give us 32 gigahertz of instantaneous bandwidth. So for continuum measurements, it's going to be very, very important. Also for multi-line work, it's very, very important. We are able to get resolutions up to 0.3. Next year with the final baseline extension, 0.2 arcsecond resolution. So good for comparing with HST type resolution. It's obvious I don't need to say this. We're going to be trying to do rotation curves, dispersion distributions, scaling relations on subgalactic scales, looking at clumps, looking at transport. All of these things that were already mentioned extensively yesterday. This doesn't come for free. You need deep integrations. And just to point out, this is what Reinhard showed you, that why we want to look at this transport, because the whole process is much more efficient at higher redshift because of the increased gas fraction, the increased dispersions. So where are we? The first one I'm going to show you is the source that Reinhard showed you yesterday. This was actually done with ALMA in the one long integration that we were able to get time on ALMA to do. And the data are beautiful. This is a CO4 to 3 map for this galaxy at redshift 2.2, a very massive evolved galaxy, BX610. Here's the CO distribution on the HST, JH maps. And you can see that we do the dynamical modeling, and here's our mean velocity field, which shows clear signatures of rotation, of course, as Reinhard told you, but we also see in the residuals, these very strong residuals, both in the data and in the best fit models that we have, that are residuals on the order of 75 or even higher kilometers per second. And with our best guess at the geometry of this galaxy, that implies an inflow rate of over 90 kilometers per second for material that's coming in and that may be building up the bulge in this extremely massive galaxy. So this is not going to become, it's already more massive than the Milky Way. This is not a Milky Way in formation. This is a much more massive early type galaxy in formation by the time it gets to redshift 0. Now, one of our best examples from Noema is at redshift 1. This beautiful spiral-like galaxy looks much more like a local galaxy, except it still has a gas fraction of about 35 or 40%. Now, the CO map that we have is here in red, and you can already see some of these issues that were mentioned yesterday, where the peaks of the CO and the peaks of the optical emission already seem to be a little bit anti-correlated. And with this higher gas fraction, those size scales may well be on order of a kiloparsec, whereas what Diederik Krausen and his collaborators have found in the local galaxies is that it's sort of on scales of a couple of hundred parsecs. So we may be able to actually trace the interesting scale for this redshift and gas fraction. Just to show you the data in a little more detail, these are our CO maps and the dust continuum map. Here is the map of the mean velocities, very regular CO signature. There may not be quite the same. There's still inflow as we saw in the other one. The inflow rates here, we do see residuals, but these inflow rates may be on the order of 15 to 20, 25 kilometers per second. And they may not be along a sort of a bar-like structure, but more just streaming in through spiral arms. But you can see the exquisite quality of the data. And one of the great things we have in the millimeter, and especially with the new system at Noema, is we've got very, very good spectral resolution. So if you go deep enough, we actually have independent channels on the scale of 10 kilometers per second. And so we can get an awful lot of information on these clump-like things on scales that are much, much smaller than our actual physical spatial resolution of about 0.4 arcseconds. So this is data, this is work in progress. We're working on this now. Of course, we're going to be trying to do this kind of analysis on these clumps in the individual channels where we heard about this yesterday. As you decrease the aperture size, you see that the ionized peaks and the molecular gas peaks decorrelate, and then with the overlap regions, you can get information about the time scales, the lifetimes of these giant clumps. And so stay tuned for that. That's something that we'll be working on this and several more galaxies. So I'll stop there and just leave up a few takeaway points and take any questions.
Thank you, Linda, for ending on a bang. Who has questions?
Hi, Linda. You highlighted the tremendous progress in molecular gas measurements, very impressive over the last 15 years. You briefly showed the Mufasa simulation prediction that suggested that at these redshifts, the atomic gas masses were dominating by factors of 3 or so. You sort of speculated that maybe tracing more of the recent inflow gas, which I think is plausible. But if I also think about the Milky Way, for example, we think that a lot of as part of the star formation feedback cycle, the gas is sort of circulating between dense molecular and more photoionized or atomic phases. So I guess I'm curious, kind of a general question, what might worry us, or what results from scaling to the molecular gas observations, might we be worried about or think more carefully about if we had perfect knowledge additionally of the atomic gas?
Also in the Milky Way, I think most of the relations, if you're trying to talk about star formation relations, I think you can, the correlation even at the Kennigan-Schmidt is much, much better with just the molecular gas alone. I mean, it's something we certainly would love to be able to consider it, but getting an actual H1 emission map within the galaxy, even at redshift 1, is going to be a challenge. I mean, there are data coming out now, but they're not very well resolved up to redshift 0.5, but it's really, really hard work. So our other thought is that once you're in the galaxy, because the gas is so dense and so rich, that conversion cycle from H2 to H1, or H1 to H2, is going to happen much faster at high redshift. But that's something, it's just I think.
Hi, thanks. At the end, you showed kind of the comparison to that tuning fork diagram that the FANG's collaboration are doing in the local universe. I wonder, by applying it to these high redshift, very clumpy galaxies, if you'll be able to say anything about, there have been a lot of claims that these giant clumps are just conglomerations of little sub-clusters that are seen in projection. And I wonder if you've thought about how that would produce a different signal in that kind of a tuning fork diagram.
Okay, so this is why what we want to do is not on the integrated map. We want to do it on the data cubes, where the clumps are velocity resolved. Okay. And because we would be able to separate out a projection effect, because our assumption is that the velocities would be different enough that we would see them. And I mean, if you look through the channels, you can see the things move around a lot. And so that's why it's so important to have the velocity resolution as well as the spatial resolution.
Yes, Linda, this is really beautiful work. Thanks for that nice talk. I have a couple of quick questions. First, following up on Andrew's question, where is the H1? That is, as you know, in trying to work out the simple model I described yesterday, we need to know how much mass is inside the effective radius. So what is the H1 to molecular gas ratio in that?
We don't know.
You don't know, okay.
Yeah.
Second question is, you briefly mentioned the effective metallicity. So I'd like you to, could you expand on that a little bit as to, are there any prospects for being able to measure the metallicity and to see how it evolves with Z, and how this would affect your mass estimates?
There was actually a nice paper out a couple of months ago by Ryan Sanders, where he has gotten some CO and some metallicity measurements. So we had tried to do the same thing with the VLT, but we're always given filler time and never got the metallicity measurement. So it's sort of hard to get a sample of CO and a sample of a reliable metallicity indicator. We've always used, in making a metallicity correction for the conversion factor at lower masses, just the mass metallicity relation, but that's, of course, not what you'd really like. You'd love to have individual metallicity measurements based on the standard optical techniques, but that has been very hard to get. All the lines that you need in one go for one galaxy, it's rather slow, and So that is something that is worked on for the future. There is, like I said, look up the Ryan Sanders paper. It came out about a month ago, I think.
Hello. Thank you very much for the talk. I was wondering regarding your last point, if you've looked for any correlation between the magnitude of the inflow and the bulge size or the bulge mass.
The correlation may not be the obvious thing, but Reinhardt, maybe you know the answer to that question because you've looked at this more on the current bulge size and the inflow rates. I mean,
I would say we need the next generation of these higher resolution maps in all respects, also in the rotation curves, okay? I mean, if you have, say, 0.3, 0.4, 0.5 arcsecond resolution, it's very difficult to separate the disk and the nuclear region. But sure, that's the goal of the next 10 years. Let's meet in 10 years.
So maybe the next speaker
He's young
could, so David could maybe start setting up. And there's one last question.
Thank you for a beautiful talk. Yesterday, I had asked about bars to the theorists. Today, I'd like to ask whether, in your modeling of the gas, is it possible by adding a bar component that the inflow you're seeing is actually along the bar-like structures, but not, let's say, azimuthally distributed in the same way? Are you able to put some constraints on how
I mean, we've been
radially
able.
distributed?
You can see things that you would say look like a bar, but we've been afraid to call it a bar because whenever, I mean, at least from what I remember, from what I learned when I was younger, is that when you're in an environment that's gas rich, you will not have a stable bar. And so
Yesterday, Arden showed us, I think, I would consider that to be a very high probable bar.
yeah. Yeah.